All right, so let's start. Hello, everyone. Welcome to episode 63 of the Warsaw Quantum Computing Group Meetups. My name is Pavel, and I will be the moderator today. Today we have pleasure to host our great speaker, Krzysztof Pomorski, who was also the speaker last week. And today he will give a talk titled Electrostatically Interacting Wannier Qubits in Curved Space. So, sounds interesting and a bit mysterious, but we'll see. And before we start, we would like to thank our strategic partners for supporting us. Sonovero R&D, Onyx, Quantum.io, Cogit, and ThinQubit. And we would like to thank our honorary partners as well. All right, I will now stop sharing my slides. Krzysztof, would you like to have this meetup interactive? I mean, can the participants raise their hands and ask questions? Or would
Yes,
you like
I,
to keep
I,
it? Yeah.
I believe it's most effective to be interactive. Yes.
Okay, good. So everyone, if you have any questions, please raise your hand first. We'll try to interrupt, and you can also post your questions on the chat, and we can ask them later during the Q&A session. So Krzysztof, thank you once again for coming, for accepting our invitation, and if you are ready, the Zoom is yours, and we can start.
Right. So, good evening, everybody. It's a great pleasure to give another seminar. Thank you to organizers for this opportunity. So, the title of today's talk is Electrostatic Interacting Wannier Qubits in Curved Space. So, let's say this topic is more specialized than the seminar given 1 week before. And this topic is purely related to semiconductor single electron devices and gives the perspective and insight how to develop such type of quantum technology. So this talk will be quite much theoretical. Nevertheless, I would say it's quite straightforward to map the presented ideas into technological processes. So this is work that is under continuation since last 4 years, and this is associated with Quantum Hardware Systems Company, and also right now it's under continuation at Warsaw University of Life Technologies. All right, so let me move on. So basically, I will talk about quantum mechanics, classical statistical physics. Then I will mention about more specialized solutions of quantum mechanics in respect to Wannier functions, and I'll mention about the different applications. One of the applications will be epidemic model. So there will be this ability to map any classical statistical physics model into a quantum model as well. Okay, so what are the main features of quantum mechanics? So quantum mechanics is, let's say, in the basic version, is governed by, uh, I would say, diffusion equation. It's with imaginary time. So this is quite much of that structure. It's linear diffusion equation, and this is usually called by physicists Schrödinger equation. Well, there are various types of Schrödinger equation, one particle Schrödinger equation, and many interacting quantum particle Schrödinger equation, and so on. And there is natural superposition of states that so like few parallel realities take place at the same time when the system is not disturbed by external observator or by external measurement in a way. And there is natural occurrence of entanglement and non-local correlations. There is a quantum coherence that describes the time of how long the quantum state lasts until it decoheres, until it loses its full quantum features. And then I will mention about non-cloning and deleting theorem and path integral approach. So basically, we have in statistical physics, we have probability of occurrence of many states and processes. And also it's less known, but in classical statistical physics, when you have the boat on the sea, this boat can can move between A and B points on various paths. This is not always fully predictive process because you have various currents, various random factors can participate. So such process in classical statistical physics is also done by path integral approach in a way. And there is a stochastic determinism so it's in a sense in classical statistical physics you can have a stochastic determinism. So nothing is fully sure. There's only probability of moving from one state to another state. So this is a kind of similarity with quantum mechanics. And of course, there is built-in intrinsic noise that you cannot get rid of. That is a part of this story. All right. So then let me move to Schrödinger equations of motion. So basically, you have Hamiltonian acting on a quantum state, and there is a dependent h bar d over dt respect to this quantum state. So it's equation of motion for non-dissipative system, and that's equal to eigenenergy that is position independent and times given quantum state. And then you can project quantum state into position base. In that way, you get position-based one-wave function. Of course, you can project on the momentum space, then you get a momentum-dependent wave function. And then you have a classical version, well, I would say the most known version of Schrödinger equation in that form. And then in general, you have dynamics that is encoded by such formulas as given by number 3. And there is a normalization of quantum state. So this is a feature of system that is non-interacting with external environment. So where you don't lose these particles when they do not escape or where they're not pumped into the system. So then there is a probability density associated with a wave function. So its wave function modulus squares its probability density at point x. And then you can always decompose complex value wave function into real and imaginary part. And in the same way, when you compute its modulus, you can have this, like I have given this here, these two factors, two contributors to this total probability. And yes, so today I will talk about a kind of dissipation from the point of view of two interacting and more interacting Wannier qubits. So you will see more involving formulas that will come quite soon. All right. So basically, what is a position-dependent qubit? So, well, you have this, it's two quantum dot system. So you have semiconductor A quantum dot and semiconductor quantum B dot. And those dots are interconnected in a way that the electron can tunnel, or a hole can tunnel from left to right quantum dot back and forth. And then the presence on the left quantum dot is assigned with logical value 0, and presence on the right quantum dot is associated with logical value 1. So and then so you can think about transistors, but it's not a must. It's an optional way of thinking. This is a way of thinking that is associated with a situation where you want to use the current state of art of CMOS technology that is highly developed. But you can forget also about CMOS technology and just be able to manufacture your own quantum dots and also have similar scheme. So when we talk about CMOS technology, then you have a transistor that has gates, voltage-controlled gates, and then drain and source can play the role of left and right quantum dot. That's a left and right localized area. That's how it is. And there is a bunch of work on that subject. So I would say first idea of this type of devices was ex experimentally implemented by Fujisawa in 2003. But even before that, also Lee Karev, uh, the father of rapid single quantum flux electronics, also considers such type of schemes. So that's not only so this concept is not that fresh in a way, but is right now under the circumstances of being reborn from the perspective of large scale applications, and that's a new path in development of quantum technologies. All right, so that's how it is. Right, then let me talk about Wannier qubit. So the so the scheme of encoding of a quantum information is quite much different from the situations where you have learned in when you use IBM quantum experience, for example. In IBM quantum experience, what you are using Transmon superconducting qubits. In other words, you are using Josephson junctions, superconducting quantum electronics. And this electronics has certain limitations, as I have mentioned already 1 week ago, simply because the size of Josephson junction is not so small. It's technically speaking, it's mesoscopic system. It's not a fully nanoscale system. It's a mesoscopic system. So it's on the boundary between nanoworld and macroscopic world. And this is due to the size of Cooper pair that is quite much big. That's, let's say, in low temperature superconductors, BCS superconductors currently used is in range of, let's say, 300 nanometers. Contrary, when you have a quantum dots, you have this the case when the sizes can be almost arbitrarily small. Let's say as theoretically almost as small as atoms, let's say a couple of atoms even. And you know the typical unit for atom is angstrom. So let's say you can downscale, I don't know, to 2 nanometers, 1 nanometer, something like that. So you have a lot of space to pack your quantum uh, uh, memory in a way. It can be very compact. But there is, of course, the price to be paid for that, and that you will see this price in terms of noise and short decoherence time. So it turns out that dynamics of two quantum dots can be described by a tight binding model as described by equation 5. And so you have the Hamiltonian that has diagonal part AP1 and AP2, this localized energy on a left and right quantum dot. And there's a Hoping term that is on its anti-diagonal part. And this matrix actually has similarities to spin qubit. So when you have spin up and down, you have magnetic fields, and then interacting with a spin, and you can pretty much decompose into such form as it's given here. You can always subtract diagonal terms, one constant diagonal term, and then you will see this direct mapping. So this is equation 5. And now there's prescription how to get equation number 5 from Schrödinger equation. So basically, if we are able to encode your system by Wannier functions, then it's linear. Wannier functions is maximum localized wave function on the left and the right quantum dot, VL and VR. And naturally, the wave function is a superposition of two Wannier functions. That's how it is. And Wannier functions are orthonormal, so they are orthogonal. Left and right is orthogonal to each other, and they have the same properties as eigenenergy wave functions, basically. And there is a prescription how to compute it. So if you know already the Wannier function, you can quite easily compute AP1 and AP2 and Hoping term. That's how it is. All right, so let me move on further. So some part of Wannier functions already appeared in condensed matter physics, but I'm using it in slightly different context. So basically, you have this two coefficients of occupancy of left and right Wannier function. So this is quite naturally modulus alpha square its probability of having zero logical state, and modulus b beta square is probability of having the one logical state. And these orthonormal values properties are specified here. And then basically you can always project Wannier function, left and right Wannier function on wave function that you are used from your various schools and textbooks. So that's a prescription given by formula number 7. But then there is a question how to get Wannier function fundamentally if you have, let's say, occupancy of two eigenenergy states in an energy-based qubit that is mostly used. So you can translate. So you are doing a certain type of rotation, and this rotation is expressed by equation number 8. So you have this cosine and sine terms, and then to get a precise value of gamma, you need to be able to maximize, let's say we are concentrating on the left Wannier function. So we are taking integral from minus infinity to x0. X0 is this boundary. It's this boundary between left and right qubit. This is usually in between, geometrically in between. But you can arbitrarily define this where one kind of logical states 0 ends and one logical states 1 somehow appears to be. So you are specifying x0, and then you try to maximize f gamma function that's given by formula number 9. And obviously, doing so, you need to compute derivative d gamma over f and set it to 0. And this will lead you to equation number 10. So the equation number 10 actually gives you the prescription for gamma coefficient. And this is done for nanowires of any topology. So let's say you can have, let's say, very peculiar shape of nanowire, semiconductor nanowire, and you can make an artificial boundary x0 between left and right side. And then you can have various interactions with biasing factors as electrodes. And then in such a system, you have naturally occurring eigenenergy ground state E1 and E2. E2 is first excited state. So in a sense, this gamma coefficient already encodes this, I would say, geometry and some realism of electromagnetic interactions in this system, especially static bias by electrostatic potential, but you can also think about vector potential bias by magnetic field. Well, here is situation described only with electric bias in a way, because this is driving factor. The qubit, the position-based qubit are driven by this electrical field, which gives you a very compact controlling mechanism in a way, because the metallic nanowires can have a small diameter, contrary to solenoids that takes a lot of space, as I mentioned 1 week before. So then you also can encode it by R coefficient. That's equation 11. But pretty much it's kind of both are quite equivalent. That's this formula that plays a role here. And then of course you can have various types of wave functions in your system, and that's just example of that. And then you can here eigen energy wave functions, and by using of their superposition, you can create Wannier functions. That's quite straightforward scheme, not so hard to be learned actually, even in undergraduate course. All right, and then we are dealing now with let us deal now with the logic constructed from electrostatic quantum gates. So this is qubit alone is the case of the A case, the left side. Then when you have two interacting lines, you can place the electron on one line and another electron on another line. And then, of course, there will be anticorrelation principle due to Coulomb repulsion. And then such system is, in quite a natural way, is logical inverter. That's how it is. And then, of course, you can generalize this scheme to various types of electrostatic gates. So you can basically design, that's a philosophy of charge boards pretty much, but then there are certain corrections due to quantumness of this structure. So this quantumness is naturally encoded in the Hamiltonian in eigenstates and eigenvalues. That's how it is. So here is another example of this how this logic is encoded. So this is case of synod logical gate. Yeah, actually, I have some ongoing work on that with undergraduate students that they will continue this type of work. Well, using a kind of similar scheme, but in more general way, you can deal with quantum neural networks, electrostatic quantum neural networks. So imagine you have the areas where the red areas are the regions of quantum dots, and the orange one are the kind of semi-insulator, and then you inject electrons propagate, and there are voltage gates, and you can think about the procedure how to learn such type of quantum neural network. So that's a problem that is on the boundary between let's say quantum physics. There's, technically speaking, it's a quantum transport. At the same time, you can functionalize this quantum transport with respect of application in artificial intelligence. And then you can be kind of sure that you're using pretty much one of the lowest possible energy for information processing. And also the sizes of the structure is presumed to be quite small in general. Yeah, so that's actually that's still open problem why people have signalized their interest in quantum neural networks. But so far, no big player has really announced massive usage of quantum neural networks from hardware point of view. Okay, there's a lot of algorithms that maps the interacting quantum gates into kind of neural networks, but this is not exactly straightforward quantum neural network. So this one, which is described here in a way, is a good candidate. This is one of possible candidate for. So one should pay more attention in that respect. All right, so that's just one of the ideas that is encoded. So actually here, technically speaking, it's also, you can also regard the system as an interacting Wannier qubits. But I would say my today considerations will be rather concentrated on the system when you don't have this interconnection. So you have this when you have two separated lines, not interconnecting lines. So that's, but still you can, even with this structure, with certain bias of C1 and C2, you can achieve separation. So that's quantum neural network concept. Let's move to more simple case. So simple case is two coupled Wannier qubits. So you have a single electron line, two single electron lines described here. And there are natural regions specify 1 and 2 that somehow correspond to quantum dot left and right. So upper Wannier qubit and lower Wannier qubit as given here. And then it turns out that you can, if you presume that the system has first and second single electron line has only two eigenenergy levels, then you can invent simplistic Hamiltonian as specified here. And then what you have here is you have your localized energy as mentioned before, AP1, AP1. So this is left localized energy of presence here, P1 presence here, and so on. And then you have additional the Coulomb interaction term. But the Coulomb interaction term here plays a kind of perturbative role. Nevertheless, of course, it's important. And they are hoping this of this. So there is hoping between for B qubit is between region 2 and 1. So for example, this term describes the energy of hoping between this and this region and so on. So that's how it is. And then there is naturally kind of, this is like, basically this is analogical. This system is very much analogical to two interacting spinning qubits in a way. So then, yeah. So then there's another question how to map this problem, because you can, in principle, you can have millions of such qubits. If you take a microprocessor, you have more than 1 billion transistors. So if you functionalize those transistors, I think you can relatively easily, somehow easily design 1 qubit, million qubit interacting system. Of course, the question is the quality of these qubits, because usually, so what people are doing right now is they take standard processes of designing microelectronics chips that usually use more than one electron actually, and they violate certain design rules. And when they violate design rules, they can presume the usage of very small charge, like 1 or 2 electrons. And then they try to functionalize already existing commercial technology into quantum technology. So in a sense, they try to commercialize classical microelectronics into quantum electronics. And this is what people, let's say, are doing right now in quite various institutes, like in Riken in Japan, in Jülich in Germany, in France, in Toronto, in Dublin, and I believe in China and in Australia as well. So there is a lot of attempt right now, and but of course this progress is never fully spectacular. So in a sense, there was a lot of achievements in superconducting quantum electronics. It's hard to beat their achievements, but somehow there is a bigger potential of usage if we overcome certain barriers. So okay, so now let me describe shortly the procedure how to move from epidemic model into the Schrödinger equation, or more exactly into position-based qubits. So let's say this what I'm calling by most, let's say, simplistic epidemic model is a matrix that can be time dependent or time independent. This S matrix acting on probability states P1 and P2, and then it's equal to d over dt with respect to this state. So then you can so this is what I'm calling epidemic model and such equation. And then, of course, you can rewrite it, because in Schrödinger equation, you are dealing with square root of amplitude of probability, and there's a phase factor. So you can rewrite it. So doing so, you can you can get in a way this terms by such type of actions as described here. So where you end, so you basically, what I'm saying is, from epidemic model, you can arrive into Schrodinger equation, into this tight binding equation, which I'm describing back and forth. That's what I'm saying. And then there is quite lengthy one of my papers in Elsevier on that. Is like almost 50 pages in length that describes this procedure in greater detail. And then what happens is that your final state, well, if you start from epidemic model, then this this Hamiltonian does depend on the phases as you see and so on. So there is certain price to be paid for such attempt, but this is somehow needed because let's say let's say you want to interact, you're a quantum physicist, and you want to interact to somebody from commercial world in a way. So let's say if you have big data, then usually big companies describe stochastic processes, and they have certain determinism of stochastic processes. They have procedure for certain type of stochastic processes. They parameterize the stochastic processes pretty much by as equation 13, this equation, and say, okay, we have a tools to this is tools we are using. We don't know quantum mechanics, but then so you can translate their algorithms, the classical stochastic algorithms, into quantum structures. That's what I'm saying. That's one of the possible paths, which is kind of described here. So it's always possible, since a quantum Turing machine can emulate the classical Turing machine, and reversely isn't possible fully. So that's the perspective. Okay, so this procedure is also described here. So this is how prescription, how to move. Yes, so there are the steps which describe because you see, when you have a quantum mechanics, you need to get rid of phase, because in this epidemic model there is no phase. So this phase has to be somehow disattached from your state. So this is so let's say if you start from this tight binding model, you want to arrive to epidemic model, classical epidemic model. So you end up with with such structure of equations. All right, maybe I will not describe it into detail because it's quite lengthy and technical, but still it's doable. I think it's a nice exercise for a student to be executed. Yeah, and let's move on. Yeah, so then we can generalize further this tight binding model, because I have mentioned to you about localized energies. Localized energies AP1 and AP2, they can have real values if they have a, since this is diagonal terms of this Hamiltonian, is somehow necessary if they have real values. Then in such case, this Hamiltonian is not is preserving the orthonormalization of a quantum state, normalization of quantum state. But if you add dissipation as possibility that some electrons can escape, then quite naturally you're adding imaginary values. And so this is more kind of realistic from technological point of view to have it in that way. So again, it can be such model, the tight binding model, dissipative tight binding model can be mapped to a kind of classical epidemic model and so on. So that's back and forth action possible. Of course, there's slightly different, more complicated procedure. So there is another way of decomposing the system into four states. So in a sense, this is like a four-level stochastic classical stochastic machine expressing the quantum behavior of the structure. So that's another way, because you have a phase, as you know, in the quantum mechanics that is non-trivial, attached to the probability density, to square root of probability density, and then again you can think about decoding the one qubit into four-level system, the kind of epidemic four-level system. Of course, this will be finally non-linear epidemic model, but that's the way it is. So here you have it. That's a prescription. So starting from tight binding model for Wannier qubit, you obtain your such. So this is your S matrix. Is this guy, and this guy. So they account for this S matrix, which I have shown to you, and then naturally this guy and this guy, they merge. So this is you have no longer square root of probability, but a probability. So that's a prescription. Of course, this procedure can be automatized into many interacting qubits, even million of interacting qubits, and so on and so on. So here, it's a feature that's supposed to be okay. There's somebody. All right, maybe I'll answer afterwards. Yeah, about the slides. Yeah, so then you end up basically in such S matrix from one Wannier qubit. So it's a structure. So S matrix does depend on the state as it is specified here. So of course, it's also natural to go into, so the Wannier qubit in code 0 and 1. You can have a qubits and generalization of qubits also in quite straightforward way. So what is interesting is that you can write a kind of similar but not the same equations of motion in such type of system. And then this is a kind of analogical but not the same to quantum mechanics. So this is from classical stochastic mechanics perspective. This is this guy over here. So this is referring to a single Wannier qubit. Yeah, so this is our kind of conclusion on this mapping procedure that is also kind of formalized. And let me move now to this curved Wannier qubits. So far, I have described you the straight Wannier qubits. And it turns out that basically, if it is possible to map three-dimensional problem into one-dimensional problem in various areas of technical sciences. So if you have, let's say, such type of system with narrow fiber, optical fiber, or you have a semiconductor nanowire, you can map such system to quasi one-dimensional, but then your real kind of unit will be associated with this length of your walking. So this is walking length in a sense. So there'll be S, I will call it S parameter, which small S parameter, which will be described later. So this is basically the imagination how this wave packet is propagating and in such systems. So the reflection from the walls also takes place, but it's naturally incorporated into effective one-dimensional approximation. So then, which principles you are using when you try to map three-dimensional problem into one-dimensional problem? Well, this is how it is. So this is S case. So this is done for two interacting qubits that are curvy in a way. So you have S1 is a distance when you move across one nanowire, semiconductor nanowire, and S2 is the distance when you move alongside another semiconductor nanowire. And then dx over dx1 can be expressed with such simple mathematical tricks in a way as described here, so and then what is interesting is when you are, for example, investigating the change of momentum, second derivative of respect to time of position, then you can write it in such a way as given here. So the curvature of the cable is encoded by dx over ds1, and there is d over dt. So you end up in the second derivative with respect to or this walking distance, but there is also the case of first derivative with d over dt with respect to s1. And then again, you have two factors that somehow, let's say, depend on the curvature of the cable, of each of the cable. So this is quite interesting to see. And the appearance of this term actually is not so surprising. Let's say you have the following problem. You have a let's say a, a wooden ball that moves in a tunnel that has small diameter. And if this tunnel starts to be curvy, the inter the so let's say at first stage of motion, the tunnel was straight, and then the ball arrives to certain curvature of the tunnel. So it has to slow down due to non-zero tunnel curvature. So in a sense, this can be also seen as kind of dissipative from a certain perspective, as this is velocity, since this is acceleration, this is velocity. So force proportional to velocity, and that there is a kind of like dissipation factor that is over here. So this dissipation is in a way uh, due to curvature. And what I'm saying, dissipation is not about losing energy, also sometimes about getting energy. So that's how it is. And this will later appear in Schrodinger equation for banded cable on the wire. And also it will even further appear in banded superconducting cable in Gisborg-Randau formalism, which I'm just going to mention to describe so deeply. All right. Okay, so let us go to this, let's say, to this main part in a way of thinking in that way. So you have three-dimensional cable, semiconductor nano cable, described by simplistic equation 22. So this is not a relativistic Schrodinger equation, no presence of vector potential. Only you have electrostatic potential encoded in BTV, in this effective potential. And this, if this, those previous tricks are allowed, I'm sorry, not this one, those guys, you can reduce this equation. You will get 23 equation number 23 that is equivalent to this equation. And here you get special types of factors. So you have curvature dependent, in a way, effective mass, you can say, because usually mass is not fully dependent on position. Usually it's not dependent on position. And you can have dependent, curvature dependent, the dissipative factor in a way. So this is encoded. So there are derivative of x, second derivative d d square over ds square acting on x. So that's this primes and so on and so on. So you get equation 23. So equation 22 is partial differential equation, linear partial differential equation, and equation number 23 is ordinary differential equation. It's linear ordinary differential equation. So this is much more simple to be solved numerically or analytically. Analytically, it's a kind of rarity in that form, but still it's somehow doable. And then it can be summarized, complexity of equation 23 can be summarized by fs function and gs function. In a sense, fs will encode you position-dependent mass, and then gs function will encode you in a way dissipation or from another perspective, actually it can encode you this, I call it imaginary part of vector potential that will appear. And then you have to be aware that from equation 22 you have Vxy xyz. This effective potential will be renormalized into new form that is Vs. So then and then the definitions of this Fs and Gs functions are which are curvature dependent are given below on the last line of the slide. So that's how it is. So that's a scheme. Yes. Then now let us consider the problem of two interacting particles with using Schrodinger equation with no presence of spin accounted for the system. It can be quite easily generalized into spin, but that's perhaps some other direction for future. And then, so you have this, so what we are presuming here is that there's equation 25. So you have YA. So in a sense, let us consider that your wire is two-dimensional, so it's bended in two dimensional. So it has a like trajectory of of this wire. So it's for A and B, and then you are dealing with solution of such problem. So there are two effective potentials VA and VB. And then there is, which depends on the gates, on this electrostatic gates. And then there is AB interaction, usually kind of Coulomb-like, but you can put more and more features into it, even, magnons and other things. And then this axion on two-body wave function. And then there is this, actually, you have these four coordinates that can be somehow reduced to SA and SB. So two effective coordinates, because of this distance when you walk across this wire gives you unique position. So this is this type of problem from mathematical perspective. So what is kind of unusual in this current form of this problem is this effective position-dependent mass that is also related to banded cable. By the way, you don't need to have banded cable to have position-dependent mass. In solid-state physics, you have highly correlated materials that might have position-dependent mass, so mass of electron or charge part of addition or a quasi-particle can depend on the direction it does move. But anyway, I'm not going that far. So this is the problem that is kind of mathematically defined. And what are possible solutions? So actually, it happens that I have the situation of, I call it, so there's quite characteristic function tangent, hyperbolic tangent. I'm using hyperbolic tangent square. So you have the cable that is straight when you go to minus infinity and to plus infinity, and it has a kind of shape like that. And then what happens is that this bending actually is almost equivalent to having the built-in barrier. So in so bending has effect of barrier basically. So it forced the wave packet to be localized in certain regions as it is seen here. And then you can additionally, so you see basically three main places of localization. And so these are probabilities for wave functions that are obtained from numerical computation. So that's one nice signal. The story of bending is not only applicable to semiconductor nanowires. You can apply it to superconducting nanowires. You can also make interesting Josephson junctions. Because usually when you have Josephson junction, you have superconductor, insulator, superconductor. So this insulator in between is this natural barrier that separates two regions. But it might turn out that you don't need to put insulator in between. You just take a superconductor on a wire and you bend it, and this bending feature almost is a kind of semi-equivalent to this insulator. So you are dealing with one piece of material that you are just shaping. That's also much nicer from technological perspective. So that's one of the directions. So we have this yeah. So I analyze various types of solutions, and usually this when you have a long straight cable, the wave packet can be very much distributed across is over a large distance, but when there is a bending, it's forced to be a kind of localized because this bending is like a potential, squeezing a kind of potential. I'm not going to discuss it in greater detail because it's quite a technical subject. And now I want to mention you about the philosophy of moving from eigenenergy qubit to position-based qubit. So you remember there was a rotation of a state. So you have an eigenenergy state. You remember this cosine gamma term and sine gamma term that I have shown at the very beginning. So if you have a Hamiltonian that describes you, the description of the system is in eigenenergy space, also you need to rotate it by two matrices to, to move to this kind of tight binding picture. So that's a procedure how for example A1 coefficient A11, this is AP1 localized energy is depending. So there is this gamma that's raised to R coefficient, eigenenergy E1, there's eigenenergy E2, and there is if you shine the pulse, microwave pulse, you have Rabi oscillations. This is and so those two levels starts to talk. This is expressed by presence of FT terms. I'm not going to describe this in greater detail, but I'm just signalizing. So there is this unique prescription for that. All right, and this is already you have seen from before. So these coefficients that are, and also you can get quite lengthy formulas. I just want to mention this is for two-level system. In more realistic way, when you have 10, 15 levels, the things become much more complicated. Nevertheless, they're absolutely doable with various computational tools like Mathematica, MATLAB, Python, and so on and so on. I'm just giving you this basic scheme. And this is how these Rabi terms for this microwave pulse can be also parameterized. Okay, and yeah, okay, so this is a kind of similar story as it was before. Maybe I will skip it. Okay, and now I want to move to something more kind of interesting. Uh, so what you can do with this type of qubits? Well, uh, you can think about lattice of semiconductor nanowires, and you can discretize the presence of wave packet in free space by presence on nanowires, and with very kind of you can create the bound states of electrons that moves on a kind of not fully circular but a kind of quasi-circular trajectories, and then so you can think about various applications of such scheme for steady and body dynamics in solid state physics, for example. Um, there's also this connectivity between, let's say, one place and another place can be regulated by this interconnectivity between neighboring quantum dots. You can apply certain blocking voltage or unblocking voltage. So you can generate your metric. So that there is certain kind of future applications of this scheme to model n-body system, and also you can think about possible relevance to astrophysics, for example, or to what extent you can think about kind of black hole-like system. All right, so let me move on. So yeah, then there is a lot of richness of behavior in such type of structures because um, now I'm still talking about these Wannier qubits, so that you have to bend the tangent square-like lines as given here, but they have a different bending case, and then the system is quite nonlinear, and for a certain period of time, you can have two particles kind of correlated or anti-correlated and back and forth. So you can have quasi-periodicity of behavior and also emergence of some deterministic chaos in the system. So that's also one of the nice perspective to be tackled. Yeah, now I just want to move to the yeah. So at least what's my message? My first message is that I'm able to mimic epidemic model or a kind of classical stochastic machine by Wannier qubits. I have the algorithm how to describe this mimicking process. That's the first thing. Second message is that I can I can I can solve problems of n-body interacting systems with Wannier qubits lattices, as I already somehow specified. That's a second thing. So third thing, I can be compatible with existing eigenenergy quantum technologies. 95% of them are like that. So since I specified the scheme as already mentioned briefly, yeah, and now let me talk a little bit about uh, the real almost the same type of problem as before, but instead of linear Schrodinger equation, I am having this uh, nonlinear Schrodinger equation that encodes superconducting properties. So you have this alpha, instead alpha and beta terms. Alpha basically supposed to be negative for the superconductor, and when you move out of superconductor becomes positive, and beta is pretty much positive in most of the time. And then, so again, this banded superconducting cable can be described in a such way as given here. So you have certain renormalizations of previously used coefficients alpha and beta, and also position-dependent mass, and also some kind of dissipative factor. Well, you can also think about, I'm not going to describe it in greater detail, about imaginary vector potential. So let's say you have Aharonov-Bohm effect present in quantum mechanics. So what is Aharonov-Bohm effect? Aharonov-Bohm effect describes the realism of a vector potential field. And the vector potential basically makes imprint on phase of wave function. And that's why it has a relevance when you have these interference processes that naturally occur in quantum systems. So moving on certain paths is more favorable, and moving on another path is less favorable. It's like interference in optics. And then what I'm saying is that I can generalize this um, real value vector potential. I can introduce imaginary part of vector potential like, and this is due to bending. This is due to bending. Here it is described as it is. This is I know that this is a little bit lengthy. So you have this imaginary part basically expressed by here by this curvature, and so I'm saying that, let's say, you can look on bended nanowire and recognize bended nanowire as straight nanowire if you renormalize effective potential V, and if you introduce additionally imaginary part of vector potential component, then you can make such 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 transformation. Well, I know it's a bit technical, so I'm not going to run into too many details. So here the formula 79, actually, so this is 78 describes you three-dimensional case, and 79 describes you two-dimensional case. So you have the banded antiquary in two dimensions. You have x, y coordinates initially, and then that's just a question of some exercise to be done for somebody who's more interested. Yeah. So I have shown you this way of reduction of a kind of three-dimensional problem expressed in nanowires or in the chain of semiconductor quantum dots. And then, so this is a way of mapping to one-dimensional problem. There's a lot of algorithms that already does exist, so that's a good message for this uh, for the way of modeling of this Wannier qubits in more precise way. Okay, there's various types of positions related to that. Let's say from my perspective, as scientist and also company representative, as CEO of quantum hardware systems, I can say that I have all mathematical methodology necessary to model Wannier qubits in very on very big scale, and in a sense, finalizing my know-how into software is not a problem. But right now, my kind of priority is to move towards real physical experiments, which are challenging technologically, and that's really one of the my priority to be pursued. In any case, you'll find a lot of description in mentioned literature. Of course, I have not covered everything. There is a lot of things that were already done before. So I would say right now it's favorable to think about non-equilibrium physics with Wannier qubits in a more special way. All right, I guess that's the core of my presentation. Thank you for your attention, and perhaps it's good to take your questions. Thank you.
Okay, great. Thank you, Krzysztof. Yeah, let's see if there are some questions. So there is a question from Marvin about the accessibility to the slides. Would you like to share your slides?
Yeah, I can
Okay,
share it. Yeah.
so you can send me the slides and I can put them on our website.
Mhm.
Yeah, and of course this meeting is recorded, so we'll also upload. Um, Hopefully, we'll upload the video to our YouTube channel. So we invite everyone to just follow it. Good. Do we have more questions to Krzysztof? So maybe a question from my side. So Krzysztof, how do you think? Do you think that this kind of qubits can, or what are the chances that this kind of qubits will lead to, let's say, building better quantum computers? So do you think it is uh, possible, certain? How do you assess it?
Okay, maybe I will say, let's say, hypothetically, let us presume that I have 10 billion of US dollars, let's say, and I want
Mm-hmm.
to invest in quantum technology. I quite honestly, I would not invest much in superconducting technology.
Mm-hmm.
This is because what was supposed to be done is pretty much done, let's say. Of course, it will always be benefit to have a slightly better superconducting qubits than already existing, but somehow you observe saturation in development, so you don't expect too many new things to be developed. It's already saturation in development. IBM Quantum Experience, and of course, Google have IBM will always have a claims they have better and better things. Of course, slightly they are better and better, but this is not dramatic. Let's say uh, game changer in a way. Um, I would say that silicon industry, uh, so in my case, maybe it was a story that I I was initially specialized in Josephson junctions and superconducting physics only. And then I just discovered this opportunity of going into Wannier position-based qubit, and I have witnessed its possible potential of applications. And that's why actually I developed my second specialization, which is semiconductor quantum electronics. And I believe that right now there is a direct company in Australia. I think this technology by constructed by direct company uh, is a good topic for another seminar for somebody to even to review the, the development of quantum products by direct company. So I would say that this is thing to be invested, and and there's also a philosophy of investment. You don't invest in overdeveloped things usually. You invest in pioneering work somehow because pioneering work gives you benefit of advantage of sudden enhancement of some technology, and quite honestly the basically development of quantum computers have also saturated. So the motivation is not so strong as it was 3 years ago. It's slight decline in investment even. So, and this is because people are repeating the same phrases again and again, and also start to be aware of this saturation. So I would definitely go in, if I am a student. Somebody said to me some very clever sentence some time ago that I don't go to a community that is overcrowded. I go to the community that is not overcrowded because then there is a space for me to occupy some area of that. If it's overcrowded, I have quite a little space by myself. So, in a sense, that's also the hint. But the very big players, like mostly when you open the media, you always get this IBM, Google, quantum universe, quantum superconducting computer. But there's a lot of work behind that already is in direction of semiconductor quantum that is not widely broadcast. And this is by Intel, by Google. I have seen already a lot of papers of them on that topic, but usually they don't share it so easily because they want to first develop it. So let's say I would really do it. And what I want to mention from Polish perspective, because we're not so big superpower in terms of industry, have to make a clever choices, and perhaps this interface between one semiconductor quantum technology and superconducting quantum technology is also a kind of prescription for some nice strategic projects to be followed. So that's what I can say. Um,
Okay, good.
I think
Thanks. Yes, yes, please go on.
there is
Yeah, I
uh,
can see there is another question from Jakub.
yeah, with machine learning knowledge can be challenging. Uh, so could you elaborate your question in more kind of detailed way, the Jakub?
Jakub, maybe you can unmute yourself and ask if you can, of course.
All right, maybe I
No,
will
no,
say.
no microphone. Okay.
All right. So what I want to say about machine learning? Well, honestly speaking, I got some signals from quantum community that quantum machine learning is not developing as spectacular as some people would expect. And actually, it's some people even start to claim it's not that deeply useful from quantum perspective. Of course, classical machine learning is very useful by itself. But let's say, I would say, if we talk about machine learning perspective, perhaps I would say this quantum neural network combined with classical neural network could could be some path to go and try to think on algorithms associated with that. So by the way, this neural network can work in a mode that is deeply quantum, but then it needs 10 millikelvin. But I presume it can work quite good at 4 Kelvin. And for cost of cooling to 4 Kelvin are not so dramatic. So I would rather think about hybrid classical quantum neural networks on single electron devices and about algorithms associated with that as a nice path. So if we talk about machine learning community, I don't believe that everything you can do with software. You need to probably a little bit act between software and hardware level, somewhere in
Mm-hmm.
between. So that's my kind of general recommendation.
Okay. Yeah, an interesting insight. Thank you for this. Good. Do we have more questions, Krzysztof? Okay. If there are no questions, then Krzysztof, thank you once again for a very good lecture and for answering our questions. And for the end, I will just share my slides for 1 more minute to announce our
Maybe
next
I will just
topic.
mention one thing.
Yes,
One thing.
please, please, please.
So remember that Nobel Prize for classical artificial intelligence was already given.
Mm-hmm.
So I don't think it will be given again. But perhaps I don't want to oversay too many things. There will be in some time, next 10, 15 years, a Nobel Prize for quantum artificial intelligence.
Mm-hmm.
But I believe that people that invented artificial intelligence, classical artificial intelligence, were physicists. They may deny it afterwards, but I believe they have a lot of knowledge of hardware as well, not only software.
Mm-hmm.
So I believe it's wrong to think only in software way of thinking. So this knowledge of physics that is quite much not so popular at most Polish computer science departments. This is a
Mm-hmm.
mistake. Physics and knowledge of physics and electronics is really essential for new algorithms, I believe.
Mm-hmm. Okay. Very interesting perspective. Thanks for this. Yeah, as Jakub said, nice remark. Good. Yeah, maybe there are some follow-up questions or comments. All right. So thanks, Krzysztof, once again, and I will now share my slides for the end. So yeah, so I would like to thank everyone for attending this meetup. If you are interested, if you like it, you can just we can just stay in touch. So we can join our groups list, follow our pages, channels, and so on. And we'll send a feedback form later today. And as I said, hopefully we'll upload the video to our YouTube channel. Uh, okay, would like to thank our strategic partners once again for supporting us and our honorary partners. You can also donate to our activities. If you are in Poland, you can donate 1.5% of your tax for our activities as well. And we would like to invite you to our next episode that will happen in 2 weeks from now, December 19th. And the plan is that there will be a talk given by a professor from IQM. The exact title hasn't been confirmed yet, but we'll probably announce it next week. So stay tuned and we'll announce it in our social media and mailing lists and so on. Yeah, thanks for that. Let's stay in touch. Thank you once again. And we hope to see you next time. Bye bye.
Bye bye.